everyone, welcome to part 3 of Flash Attention, where we're going to discuss about the overall algorithm used for Flash Attention. I'm talking about Flash Attention V2, and there is also a paper released Flash Attention V2 couple of months back, but I'm going to discuss about the algorithm of Flash Attention V1. In the first two videos, let me go through that. In the first two videos, we have discussed about how a GPU generally works on a very high level. Also on a high level of how a flash attention works, what is a workflow and what is a control flow of flash attention. We will also go through these two in short, but if you would like to get to know more about that, just go through these videos as well. Okay. So we'll go through the GPUs and other related stuff at the beginning in short. So as you know, the data lies in the hard disk, and if you want to execute that data, if you want to run some operations on the data, that has to be there on the RAM, and this data goes through the memory hierarchy and finally it reaches a GPU. And flash attention, whatever the algorithm they talked about, the optimization or the fastness, it is all with respect to GPUs and not with respect to any of the RAM or L1, because in the paper as well there are multiple times L1 and L2 L3 caches are mentioned. Those are all with respect to GPUs and not with respect to RAM or L3 L2 cache. Okay, and once the data reaches GPU here, and we also have a similar memory hierarchy here, it has L2 cache and it has something called streaming multiprocessor, and it can have multiple streaming multiprocessors, and each streaming multiprocessor, or in short SM, can have optional tensor cores which are much faster, in fact like 200x faster than the GPU memory which you have here, and it can also have optional CUDA cores, registers, and etc. So overall flash attention tries to make use of the tensor cores, because it is also found out that while training GPT-3, 50% of the time tensor cores are empty. So whatever the efforts flash attention does, it is to make sure that the tensor cores are utilized properly, or much more utilized than 50%, I could say, right? And flash attention is also one kind of algorithm which is not an approximation, as the title of the paper itself says, it's an exact implementation. Okay, and flash attention V2 concentrates more on the verbs and how to schedule it and other related stuff. So this is with respect to flash attention, and let's have a look. I think there are various benefits as well. So in short, I think it uses mainly two concepts flash attention. One is something called tiling, and there is something called recomputation. Tiling as in, each token in a transformer have three matrices Q, K, V, and these are big matrices, and instead of reading all three metrics from HBM memory to the tensor core, why don't we split it into chunks and read by one? That's what called tiling in short. And recomputation, we know obviously we need to backpropagate, right? Instead of storing the values in HBM memory and reading back from HBM memory to tensor cores and do the backpropagation, why can't we just recompute even in the backpropagation, right? And that's called recomputation here. And of course, when you do the recomputation, number of flops, that is floating operations, would increase, but we know that float the amount of time it takes is much shorter than a memory access, than a access to the GPU memory, right? So these are the major two concepts which flash attention uses to get the things done. Now we will look into the algorithm details, whatever mentioned in the paper. So first let's get started. As I was saying earlier, it uses one of the concept called tiling, right? We have QKV matrix, and we need to divide QKV matrices into blocks. So how do you assign it? In one of the talks, the author mentioned that 128 is the matrix size which was being used, or you can say block size which is getting used here. So now whatever the BC and BR you are seeing in the first line, it is just to get what should be the block size of Q, K and V matrix. Okay, and also we need to initialize few of the intermediate variables, you can say. For example, intermediate variables in this case could be L and M. What is M and what is L, we will discuss this down the line in very detailed way. Okay, and finally O is the output, because in the tiling we don't read big all the QK matrices into the tensor core, right? We will split it individually, then we'll do the operations on a chunked QKV vectors, and we need to store the intermediate results in the variables L and M, which would help us in getting the results later down the line, because we need to combine all these intermediate variables to come up with the final output, right? That's why these intermediate variables are used. So after finding the sizes of the blocks, we will divide Q, K and V accordingly, and then after, even similarly, we also need to divide the variables as well, right? We also divide O, and also we will divide L, or we will divide the L, and we also divide the M, right? If you are getting confused what I'm saying by L and L, please be with me for next 10 minutes, everything will be crystal clear. Okay, then we will go through each of the blocks, in this case QKV, right? How we will go through is, we will load K and V blocks from HBM memory to on-chip memory or SRAM. Once it is loaded, we will load query blocks one by one, and then all of these intermediate values will be calculated. That means on chip Q will be loaded here, and then Q and K will be multiplied. Of course, we will get something called attention scores, and after that we will do the, we need to subtract the maximum from the whatever the multiplication, of course scale down, and finally we will get something called attention scores or attention weights. Then we need to store these attention weights, whatever we have it here, into the respective variables, in this case L, M, etc. What is M? That means we know, let's look at the softmax formula here for a while. This is what the softmax formula is, and we know that this formula is used in transformers encoder as well, right? So now this is a plain softmax function, but this has some problem. That's why what we usually do is, we will try to find the maximum from the input vector or from maximum value from the input matrix. We'll try to subtract it. That's called a safe softmax. We also discussed that in previous video as well. We will also discuss that in detail in this video, and then all this will be summarized just to overcome that underflow or overflow. These kind of errors won't happen. Okay, and after that, L is something called a denominator, whatever we are seeing here. L is a summation of, we need to go to each of the elements and then e raised to that element minus the max. That's what the L is, and that is with respect to only the blocks which has been loaded. Okay, and then finally OI will be calculated, that is the output, and that's also returned to the HBM. Similarly L and M values as well, right? And just I know this formula is kind of bit tedious to understand, but if you look into this is like it seems like a very complex algorithm, because we have a lot of chunks here. We're not sure how the chunks are collated together to come up with a big output, right? Because I was saying that softmax is being used, but if we don't go through all of the values of QKV, how are you going to calculate these values, right? That's the biggest question which you have. So even in this paper, there is another paper which is released, which is a basics for this algorithm, I feel. That is from NVIDIA. It is called Online Normalizer Calculations for Softmax. This is the paper which is also referred in this FlashAttention, where this paper is also one of the beautiful paper as well. So where they discuss about, if we have a softmax function, if you have a, let's say, list input array, let's say we're having 10 or 20 or how much ever is that, how we can split this big array or big list into chunks and calculate the operations individually and then combine it to calculate the softmax, right? Basically, if you want to calculate the softmax for a given array, we need to know what is the, let's say, maximum element, or we need to go through the element one by then and then e raised to whatever the element is and sum it up, and then we will come to know the denominator. Only once we know that, we will able to calculate the softmax of the given input array, right? But this paper shows that how well we can calculate, even we need not go through all of the elements all at a time, right? We can also go through the input array chunk by chunk, and we can store the intermediate values, and then we can make use of these intermediate values to come up with the global softmax values, right? So this, whatever the algorithm showed by FlashAttention v2 is also highly influenced by the NVIDIA paper, which is online normalizer calculation for softmax. Now we'll just go through this as well. As I was saying, this is a standard implementation of softmax where each of the elements, it will be raised to exponential, and sum of those exponential will be in the denominator, and whatever the elements we get, that we call it as approximation of probability distribution of elements, right? And now this is how the naive implementation of softmax will go through these elements, and then we will rise it to that and keep on summing it up, and once we do the summation, we will just rise it to the power and divide it by this number. It just normal softmax whatever going through that. As I was saying few minutes earlier, this method has a problem of overflow or the underflow, right? Because these values e raised is exponential, we all know it. It could be so high that whatever the values it returns, we might not able to store it, or it could be so low that even we might not able to store it. These are the two extreme ends, right? That's why we usually go with something called safe softmax. What it does is go through the list, okay, try to find the maximum element from the list, and then subtract that maximum element from each of the element in the list, and then you raise the exponential power to that element, and then just sum it all, that's what your denominator, and then calculate it, right? This is also mathematically proven that this also works same as this, and but it doesn't have the overflow or the underflow problem which we used to have it here. I think we also had discussed the few of the examples in last video as well. Let's say we have this array, big numbers here, and then what I'm trying to do is here softmax function. Let's say this is the input array 2 4 1 etc., and then you take exponential of each of the numbers, right? And then when just try to print it, we know that these are very big numbers, even it is like inf here, and then for each of the raised exponential, we are divided by the sum of those exponential. In this case, it's e raised to 2, e raised plus e raised to 4 plus e raised to 1 etc plus e raised to 100k, and finally this is what the softmax output looks like, vanilla softmax. As I was saying, we cannot really read about these numbers, right? That's why something called safe softmax which is here, that means softmax with maximum value which is getting removed. Similar operations, but all we are doing is just subtract the maximum here. We know this is the inbuilt function in Python. How it does it, it will go through each of the elements in the input array. In this case, it will go through each of the elements in the array. It will try to find the maximum, in this case 100k, and then it will subtract 100k from each of the input elements, and then rest of the operations remain same. But as you may see here, there are no overflowing errors here, there are no there are nans here, but I think in this case there are no nans or no overflow here. There are no invalids also here. Moreover, I think this took like 300 milliseconds and this has taken 3.9 milliseconds. There are a lot of differences, right? So this is with respect to safe softmax, and most people, I think, we are aware till here, I believe, right? So let's have a look into the how a safe max is. I think we look into on a high level how it is implemented, right? Let's have a look into the algorithm of how a safe max is implemented. Okay. So this is the low level implementation of safe softmax. So we will, so we all know the safe max or safe softmax formula, right? First of all, we need to find the, I think if you look into this formula here, okay, it will go through each of the elements in the input array and then it will try to find the maximum element, right? And that's what the first for loop does. It will go through each of the element and try to find the maximum of all the elements. Okay, and then we can also see that there is something called summation here, right, which will go through each of the elements, that will go through each of the elements xj, and then it will subtract the maximum value from the input array to that element and exponential to the power and then addition on top of it for all of the elements, right? That means each I think this is how the formula goes. It will go to each of the elements and then that element is being subtracted from the maximum or vice versa, sorry. That means maximum value which you have found out in the first for loop is subtracted from this element and e raised to that, right? And we will do the calculation for each of the elements and that will be stored in something called dj. Okay, and that's the second for loop. And third for loop goes to again each of the elements in the input array and whatever the element we calculated here, that is maximum mk and dj, that will be used to calculate the final softmax values here. Now there are some, you know, matches we can do it with this algorithm with respect to the flash attention here we are having. So here we have something called mij, right, and row max of sij. Why ij? Because we are dealing with metrics, right? And here we have mk. Why? Because it's a simple softmax. It's a one dimensional array or one dimension list. So but more or less it's talk about maximum element in a given matrix or in a given list. That's what m stand for, right? And if you also observe, there is something called, they are also using L, right? L you can equate to whatever we have dj. So if you look into the algorithm what I have mentioned here, even to calculate softmax they have L here, Lx, right? I'm not sure why they have used L as a variable. I feel D makes sense. D makes more sense because simply you can call it as D for denominator, right? I'm not sure really for what is L is. So you can just match it, yeah, no, DJ for D for L and M for maximum. Okay, and Y is the output, and here we call it as O. Just simple as that. Now, if you look into this, there are three for loops we are having. Asymptotically, the time complexity of this overall algorithm is order of n. We are also going through all of the elements here plus same of the elements again, same of the elements again, right? Three for loops, it is order of 3n. Asymptotically it will becomes order of n. But if you look into the number of memory access being made to the HBM memory or called the GPU memory is very high, and we all know that from the study of GPUs. We also discussed this in the first part of the video, that memory access is the bottleneck for the slowness of the transformers, right? and that is what the paper of the title itself says, that it's IO awareness, right? So now, for this, coming back to this, to have this work, to make this safe softmax work, there are four memory accesses which are done. In the first for loop, it is just a read, right, each of the elements and to find the max. Again on the second for loop, again we are reading it. Even in the third as well, we are reading it, plus we are also writing it back. So it's 3 plus 1, 3 read plus 1 write. There are 4 memory access, which is a bit huge at the low level. So what the author says is there any way we can reduce this number of memory operations or memory access operations, right? And now the problem boils down to typical algorithm and data structure question. That means, is there any way, not asymptotically, is there any way we can reduce the number of memory access elements? In simple terms, is there any way we can merge the for loops which are shown here? Maybe we can merge this and for loop, or maybe we can merge this for loop with this. Is there any way we can merge the for loops and have single or two for loops which does the same job, right? And it seems like they have found out a algorithm which does it, and we are going to look into that algorithm too, right? It is called online normalizer calculation. The calculation just happens on the fly, or you can say online, on the fly. We will look into that, how it happens. Okay, so now this is what the online normalizer calculation algorithm looks like. If you are a lover of algorithm, or if you are a lover of overall data structure algorithm, you would really love this. Okay, so now, okay, what's the agenda here? I think we need to find a, one second, we need to, yeah, basically we need to get this done, but not using 4 memory access, but we need to do the exact same thing but with less number of memory access, right? We should not forget that. So now if you look into this on a high level, we have 2 for loops. Okay, earlier we had 3, now we have 2, and of course we have first for loops, which will go through each of the element and tries to find the maximum. There also we have done the same here in the first for loop, whatever it has done here, and the same, more or not more or less, it is exactly the same thing, right? And there is one line addition here. We will discuss this, what is that, in depth, but we'll skip it for now and we'll go to the second for loop. What it will do is, whatever the operation the third for loop in the safe Softmax does, exactly same thing this for loop is also doing with the online normalization. That means go through each of the element, subtract the maximum value from that element, e raised to that element, and divide by the sum of those, right? But now, how do we how do we get the denominator at the first place itself, right? I think dj, or in case I think final value is dv. I think one of the catchiest thing is how are we even calculate this, right? So for this now, if you look into this, always previous values will be taken and it is multiplied by with previous max j, and then finally it is divided by current max, and then e raised to x and minus I, right? I will try to explain this with an example here. So we will look into this example bit later. Okay, so now let's talk about the intuition. Let's say we have an array of 3 4 5, okay, or a given list of 3 4 5. How do you calculate the softmax for this, right? Save softmax. Now maximum value is 5, of course, right? And if you want to sum it up, e raised to here, e raised to 3 minus 5, because that's the maximum value here, and e raised to 4 minus 5 and e raised to 5 minus 5, right? Because 5 minus, because that's what the maximum is. Now there is a formula of like if e raised to a minus b is equal to e raised to a divided by e raised to b. This formula I am applying it back here. So after applying that, this overall equation will boils down to e raised to 3 plus e raised to 4 plus e raised to 5. That means e raised to power of all of these elements divided by e raised to of maximum element. So far, right? So far, why means let's assume that this array is keep on continuing. I'm just taken only first 3 elements in a given array, right? Let's say in the 4th iteration, right, a new element we come across, let's say that is 10 here. Okay, so far we have this exponential sum which is calculated, all good, no problem. Let's say if I enter a new element 10, how are we going to modify the one which is already calculated to compensate to this? Okay, and this is what this formula is trying to do here. Let's have a look into this. So whatever we have previously, that means e raised to 3 4 5 plus we are multiplying with e raised to 5. Why? Because till here, what was the maximum? Till here maximum was e raised to 5, right? That we already divided by, I think we already divided that with the sum because that's what the Softmax formula. But now we found out that, hey, we already found a new number 10, right? That means we need to undo the changes whatever we have done here. We had earlier divided by e raised to 5. If we want to undo this change, what we should do? We should multiply it by e raised to 5, right? And then we know that new element is 10 and maximum is also 10, right? And then we need to divide it by the e raised to 10 plus this is whatever happened so far, we are undoing the changes, and now e raised to the new element divided by e raised to maximum. It so happens that in this case both are same. That means that e raised to 10 minus 10, that's what it is trying to say here. Okay, now if we solve this equation, e raised to 5 will get cancelled here, and then e raised to 3 4 5 divided by e10, and then e10 by e10, and overall this formula will be not formula, all the equations boil down to e raised to 3 plus e raised to 4 plus e raised to 5 e raised to 10 divided by e raised to 10. Because why 10? Because that's what the denominator is, right? And overall if we do it, whatever we get exponential sum, right, this is what the denominator is. In our scenario, this paper, NVIDIA's paper, it's called D. In our FlashAttention paper, it's called L. That's why you see L in the denominator here, and that's why we are also having denominator here, right? So in short, every element, as you can see, we are undoing the previously done changes. What I mean by undoing, right, whatever the maximum element through which we had divided it by, in this case we had divided it by e raised to 5, we are undoing the changes by multiplying it, and then you are adding e raised to 10, which is the current maximum. By doing this, we can avoid going through the elements of an input array twice. That's what this NVIDIA paper has done it. Instead of going through one more for loop just to find the sum denominator, they are doing the same thing in a single for loop. That means now we will try to understand this. So denominator, previously whatever the denominator has been calculated, we are multiplying with the previously calculated max value. That means in this case e of mj minus 1. That means in the previous iteration mj minus 1 was the maximum. That's why we are undoing it by multiplying it, plus we are also divided by the e raised to mj. We know that e raised to a minus b is equal to e raised to a divided by e raised to b, right? And then this same formulas goes for here as well, but this is for the older one. But what are you going to do for the newer one? Even if there is a one element, that will be e raised to that element divided by the maximum of it, right? We're just adding on top of it. So by doing this, number of memory access has reduced from 4 to 3, that means 25% it has reduced, right? So this is with respect to how the can say intuition of the safe softmax, which is on the low code level, right? But we'll also look into the few of the examples as well. I think now I will get back to some of the examples I have taken here. We'll go through this quickly. I think it's now, after understanding this while undo thing, and then this becomes literally a cakewalk. Okay. Now this is a safe softmax formula, and this is the what do you call this as a low level implementation of that formula, right? And we are using m and do as an intermediate variable. M, maximum value of the given input array calculated so far, because on the input array we are calculating on the fly, right? It's called online normalizer, right? So far, what is the maximum value? D0 also denote the same. What is the sum of the denominator calculated so far? Let's say this is the input we are having 0, 1, 0, 3, 0, 0, 8, and these are the default or initial variables. In the iteration 1, of course, right, I think x is equal to 0.01, that is first element we are considering here. What is the denominator sum? It is 0. Now we are trying to find maximum value, because that's the only one element we have seen so far, right? And that itself, and previously we haven't computed anything. And for a given element, softmax of that will always be 1, and that is it. D0 is 1 here, previous is equal to, and whatever we calculated is now 1 will become the previous, right? I'm just reshuffling this for the next iteration here. That means now in the next iteration 03 is our x, and D0 is 1 because we calculated previously. M is 0, 1, that means in the previous iteration whatever we calculate is 1, and previous m is also obviously 1. Now let's calculate this. M is equal to max of 0, 1, 0, 3. Why 0, 1, 0, 3? It's maximum of previous maximum versus current maximum, right? And here it is 0, 3. Now here, as I was saying earlier, previously calculated D0, we are undoing the changes whatever we have done it on the earlier. That means exponential of 1. That's what earlier we had divided by. Now we are multiplying it to compensate, and then we are divided by the e raised to of 0.3. Again, I'm not repeating multiple times, but e raised to a minus b is equal to e raised to a divided by e raised to b. Keeping that in mind and going ahead, and exponential of the element which is x here minus the maximum here, which is found out to be 0.3. If you do this calculation, you will get like 1.81 etc etc, but I'm just rounding off to 1.8 for easy calculation, and previous sum will also be updated. In the iteration 3, same thing happens. Now we are x is equal to 0.008, d0 is 1.8 because that's what we had calculated so far. Previous m, that means so far what is the maximum we found out? 0.3, right? Now if you compare to that 0.3 versus 0.008, which is greater? Of course 0.3. We were keeping the same thing as it is. Now previously I was saying that we need to undo the changes, right? Now if we look into here, we are trying to undo the changes with the same formula, but this positive put into 1. Why? Because absolutely there is no update in the maximum, right? if there would have been a maximum, then it would have never been equal to 0, right? That's I think one of the observation we can make. And here there will be of course e raised to the element which you are currently addressing divided by the maximum element so far found, and rest of the remain the same. So one of the observation we can do it is, whenever we find a maximum element, because in the second iteration we found a maximum value, right? The first part of the equations updates, and whenever we find an element which is not the maximum element, that's where the second part of the equation updates. Okay. If you're not understanding the flow, just go through this video one more time so that you will have a better understanding of what I'm trying to even say here. So let's have a look into the Pythonic implementation here. Okay, this is Softmax with online normalized calculator here, and whatever I've explained here I've just noted down using a simple Python functions. But I'll just skip this part in the interest of time, and I will directly go to the next part here. That means, given a list, how are you going to given a two list, how are you going to calculate softmax separately and then combine it, right? For me, when I look into that, it is like a, wow, how can I even do this? Because it falls onto algorithmic question. For to explain this, I have taken one random list here, and then I have divided into two sublist, input list 1 and input list 2. Okay, so we'll process the first sublist, and then we will process the second sublist, and then finally we will merge the list. Okay, in the first sublist, as I was showing earlier, we are gonna calculate, there is something called M0 and D0. That means basically what? M means maximum element, D0 is the denominator, right? Using this formula, whatever I have shown in the here, the same formula which I am using here, we will calculate a D0 and M0, and then I am just calculating the O0 here. Why O0? M0, D0 is fine, but we also need to apply whatever it has been calculated, Mn, in the next for loop, right? That's where we can convert the input array to the softmax, right? So now this is where the second for loops comes in. We are making use of M0 and D0 to calculate this, basically maximum and denominator. You just fancy things, and then summing it up, obviously it has to equal to 1. Now taking couple of steps back, if you want to back map it to the FlashAttention algorithm, we have the O here, right? In this case I'm also having O, that means I'm calculating the softmax, but what they're doing is, we have this scale down operations and Q into K, all those stuff, plus the softmax, all they're doing it, storing it in OA block by block. Here I'm doing also block by block, but not at a matrix level, but at a vector level. Okay. Now we have, so first sublist we have M0, D0 and O0. Similarly, we will process the second sublist as well. We will get M1 and then the D1 and then O1. Okay, and this is where the fun comes in. Now this is what the input list is. Okay, and we will, for the from the first list we have M0 as the max element. From the second list we have M1 as the max element. Let's try to note it down here. Not note it down, let's execute. That means from here, from here to 0.45, yes, correct. From here to here, this is 0.5, right? We are trying to find the maximum of these two, which is obviously 0.5, correct? Now applying our logic once again, right? So NP of whatever the I think this is also, you can note it down to, whatever the maximum value found so far for the first array, that is maximum value found for the first array so far is m0, right? We are undoing the changes. That means we are e raised to m raised to 0 we do, divided by the real m, because this is what the real max, right? Plus we are also doing the same thing for the m1, that is the second right side, right? Because second half of the array we had multiplied with the maximum of the second half of the array, but when you look at the real m, that is 0.5, right? We are also undoing the changes, and for the d1, right, denominator, and finally we calculate the d new. Okay, we had m0 d0 from the first array, we had m1 d1 from the second array, and then combining these two we have real m and d new to come, that is like a overall full array, right? And finally we calculate the O new using the whatever the calculate values here. That means here in this case it is like a real m we have calculated, that means here in this case 0.5, and also we have d new here, what is the new denominator, right? Using these values the softmax will be calculated for the first subarray, that is O1 new. We need not read whole array again, we're just taking the chunk of the softmax, we chunk of the input array, we're just applying this, what you call it as merged matrix or merged variables to the separately to the arrays, right? When you do this we will get these are the values here. Same thing you do for the second half of the array or second half of the list, you will get this second list, right? Where if you observe it, we are calculating the softmax for each of the elements or softmax of a list, not loading all of the input list into RAM. We are just dividing it here and then calculating it, right? So now how do you verify this? Of course, right? I think if you add all of these, it should boil down to, it should sum it up to 1, correct? And that is exactly it is in sum of O new and sum of O2 new, it is equal to 1, because the sum of softmax, it has to equal to 1, otherwise it won't be a probability distribution, right? And then just as a verification as well, I have calculated softmax with a whole list as well, right? Whatever the list we have, just do the normal softmax calculation to see how the values differ. So this is what the values looks like if we take the whole. But now O now, that is first half of the array, this is how the values looks like. And even if you take the, when you take the all of the array and calculated this is the first 4 elements, right? If you look into this, these are like 99.999% these are same, just that very minute differences, that is because of some decimal rounding ups or something. Otherwise it's very it's not, I think I would say like 100% same. And this is what exactly the formula of whatever I was showing from the NVIDIA does here, right? Even for the second half of the array, if we look into that, if we calculate the softmax by taking full array, full list, this is what we get. And the for last 4 elements, if you divide into chunks and calculate separately, this is what the value you get. Exactly same, right? So this is it. But I think the aim of the video is to explain this specific, and I believe that whatever, if you just understand this overall safe softmax implementation low level, we should be good enough to understand what is happening at the high level. So try to watch this video once again. In any case, if you are having a doubt or even if you get confused in the middle, just go through that couple of times. I'm sure this will be clear. Okay. All right. Thank you so much for watching this video.